Welcome everyone. Thank you for joining today's webinar, To License or Not to License, Selecting the Right Frequency for Your Application, co-hosted by ISA and Eaton. My name is Stacey Logan. I'm with ISA and will be hosting today's webinar. Before we get started, I'd like to review a few housekeeping items and let you know how you can participate in today's session. First, for questions. Please submit your questions at any time throughout the webinar. We will hold your questions until the end during our Q&A session. To submit your questions, simply type them into the Q&A box on the right-hand side of your screen. If you're viewing along with others at your site, please designate a scribe to submit your group's questions. Unfortunately, with this large of a group, we cannot open the phone lines for questions. If we do not get a chance to respond to your question, or if you would like to discuss a topic in more detail with one of today's presenters, please feel free to contact them directly. That information will be given at the end of the webinar. Second, for those of you who have just joined, please make sure that you are on mute. Both your computer and phone microphones should be on mute. If you would like to see the phone connection instructions again, please refer to the confirmation email I sent you earlier today, or if you go to the top left-hand side of your WebEx screen, you will see a tab labeled Meeting Info. All of the connection instructions are included there, including contact information for me if you are experiencing any technical difficulties. If you have any questions for me, the presenter, submit those into the chat toolbox. All questions for the Q&A are to be entered into the Q&A box. Okay, I think that takes care of our housekeeping matters, so let's get started. I'd like our first presenter, Brian, to take it from here.
Great, thank you, Stacey. My name's Brian Cunningham, and I'm dialing in from Vancouver, BC. And here's a quick bio, my history. I'm a graduate of the British Columbia Institute of Technology, their electronics technology program with a specialty in process automation and instrumentation. And since then, I've been working for what's now 23 years for a variety of different companies in the automation field. Most recently, I've been with Eaton Corporation. However, originally it was called Omnex Control Systems. Omnex was acquired by Cooper Busman. Cooper Busman was acquired by Eaton. So now I work for the Wireless Solutions business unit with Eaton Corporation. The main role here of myself with Eaton is applications engineering. In other words, helping users design, commission, and troubleshoot industrial wireless systems. And now I'm going to turn it over to Dick to introduce himself.
Very good. Thank you, Brian. This is Dick Caro. I have my own consulting company, CMC Associates. My educational background is BS and MS in chemical engineering. And I have about 40 years of experience as a user, where I worked in the chemical industry and also the pulp and paper industry, as a vendor, where I worked for what was at the time the Foxborough Corporation. And now I have experience as a consultant, having worked for Arthur D. Little, and now on my own. Been with ISA for some long period of time. I have an ISA CAP, which is the Certified Automation Professional status. I am an ISA Fellow, and I've been elected to the Process Control Hall of Fame. Additionally, I have written 3 books, all of which are available from ISA, and you can see the names of those 3 books, including ISA's first book on wireless. And with that, I think we can turn it over to Brian to introduce the agenda.
Great. Thanks, Dick. And I just wanted to point out to everybody, it's a real pleasure to have a very highly qualified gentleman with as much experience as he has with Dick able to join us today. So thank you for joining today. Here's what we'd like to chat about today. First of all, we want to introduce the reason why we're presenting this webinar. In other words, the application problems that some customers are facing when they go to deploy wireless systems. Next, I'd like to chat about standards-based radios. And then we'd like to talk about where those standards-based radios are being used and how and where and this sort of thing. Then we'll chat about how we do longer distance radio links, typically outside of the plant. Then we're going to jump on to frequency selection and some of the different options available. Then we'll chat about the pros and cons of these different radio types. Next, we'd like to introduce cellular modems and show where they are now making their mark in the industrial world. And then we'll chat about hybrid radio solutions, where we're combining multiple radio technologies together to meet a customer's needs. And of course, then we'll have our Q&A session and wrap things up. Okay, so jumping right in, the very first issue is the application problems customers are facing. In this picture right here, this is a screen capture from a spectrum analyzer that I took just outside of a Phillips 66 refinery. And this is showing the 900 megahertz band. And what we're looking at here, this is a very, very high level of interference. In fact, it's very rare that I will see this much interference in a particular location. The top half is showing the magnitude of the interference, and the lower half, the waterfall, is showing the duty cycle, a near continuous duty cycle of interference. So this is showing that there can be some issues utilizing the license-free 900 megahertz ISM bands. So one of the issues we're running into is that those bands are getting a little bit crowded, that there's lots of users installing all kinds of equipment in those utilizing that spectrum. The other issue is that sometimes the range isn't far enough. People can't transmit or accomplish the distances that they would like to be able to do. The next issue that we're running into is that high throughput applications need lots of spectrum. So what do you do if you want to transmit a great deal of data at a very high baud rate? And then lastly, keeping in mind that we all deal in the industrial world of refineries or plants or water wastewater businesses. These run 24 hours a day, 365 days of the year. So high reliability is a key requirement here. So keeping that in mind for this entire discussion here. Okay. Now with that, I'd like to turn it over to Dick, who is our expert on standards, and have Dick chat about some of the standards that we are seeing in the wireless business.
Thank you, Brian. Standards being applied in many areas of the industrial automation business, and some of those standards depend on the particular types of interest or application problems involved. Particularly the segments of the industrial automation market are usually classified this way into process control section, which describes continuous and batch manufacturing in the chemical, petroleum, refining, metals, food, pharma, pulp and paper, cement, glass, steel, and a whole bunch of industries like that. And then separately, there's the discrete parts manufacturing, sometimes called factory automation, part of the industry. The application is often final assembly and test. Sometimes it's machine tool operations. And it's identified by industries such as automotive, white goods manufacturing, which includes home appliances like refrigerators, stoves, washing machines. Also includes warehousing, bottling, canning, and many operations such as those. Now, also included in the industrial automation area, although sometimes regarded as a separate entity, are the building automation activities and also electric power generation. These share a great deal of similarities to the process control and factory automation areas, but are not usually included, but we will in this presentation because there's some significant applications in wireless for those. Now, one of the problems of doing a standard is that we would like to have the same set of frequencies and in the same, that is the frequency allocation, in more than just one area or country of the world. The standards are often done so that they can be used anywhere in the world. And unfortunately, with the radio spectrum, it's usually allocated by country. But the countries of the world have all agreed to not assign a certain set of frequencies, but allow those for public use. And those are called the ISM bands. And ISM stands for Industrial, Scientific, and Medical. These bands do not require a license. They're generally available worldwide. Therefore, when we design for mass market or volume applications, we typically assign a frequency within the ISM band. Now, there's two ways to develop standards, and this is all standards, not just wireless. You can develop a standard using an open standards committee that's been affiliated with one of the standards making bodies. And when you do that, then they're governed by the international rules of standards. And accordingly, it must be a non-competitive environment, and it must allow user involvement in some way. An alternative way to create a standard is for a consortium of vendors, and that's often led by a single manufacturer, will prepare a set of specifications and then drive it to market so that they can take advantage of it. And while that's happening, they will also submit it to standards organizations. So both of these methods have been used, and I might say that users are usually involved with the consortium, not at the beginning, other than the fact that the consortiums know that they have customer problems to solve. But users are usually involved at the testing side. Now, I'd like to look at the standards that have been done recently in the wireless area. The first one I'd like to talk about is ISA 100. This was developed by ISA 100 Standards Committee, and it was it became an American national standard as NC ISA 100.11a, and within the past few weeks it became an international standard, IEC 62734. This standard was based on yet another standard that came from the IEEE, one of their personal area network standards, 802.15.4. And this standard specifies the radios to operate in the ISM band using direct sequence spread spectrum. And it also uses AES 128 encryption. And what that means is that the encryption key for this standard, which is a U.S. government originated standard, is 128 bits long, generally regarded today as unbreakable. To that particular standard, which has existed since 2006, we added additional features called channel hopping, which is amongst the 16 channels that are assigned. We added source and graph meshing at the medium access layer. We added duocast messaging for redundancy. And we incorporated the 6LoWPAN, which is an internet standard, at the network layer, and we specified UDP-based transport layer, another standard from the Internet. In addition to which, we specified an object-based application layer using an IEC standard 61804. So as you can see, we have prepared a standard which is strongly dependent on the use of other standards as well. Now, competing with ISA 100 for the same applications is wireless HART. And wireless HART is defined by an IEC standard 62591 based on HART 7. This was created by the HART Communications Foundation, a consortium of vendors selling HART instruments. And it was prepared by them and then submitted to the Standards Committee. This is also based on IEEE 802.15.4 in the 2006 version, again using spread spectrum radio and AES 128 encryption. And to that, they also added channel hopping amongst 15 of the channels, 15 being because those are the 15 that are usable worldwide. And they added source and graph meshing at the network layer, a little bit different. And they added a proprietary transport layer. The application layer of wireless HART strictly is devoted to HART 7 commands. Now, wireless applications for factory automation have been strictly based on the use of Wi-Fi. Wi-Fi is the same 802.11 protocol that we use on our laptops and our cell phones, smartphones. And it's basically the applications in factory automation are those that have been adapted from the earlier Ethernet applications, where they are simply using the Wi-Fi as an Ethernet extension. And they've added no particular features or uses of the wireless other than to use it in either cost savings mode, where wiring would be more expensive, or where it's really not practical to use a wired connection, such as to cross a public way or other reasons. They use TCP/IP protocols, and there's one example of process instrumentation or factory automation instrumentation that uses Wi-Fi as its basic transmit medium, and that's some products made by Siemens. Usually these are interfaced through one of the Ethernet-based protocols, and the two dominant ones in factory automation are Ethernet IP and Profinet. There's some emerging technologies that are using 802.15.4 based on additional upper layer protocols defined by the Zigbee group, applications group. And then there is a set of contact limit switches, proximity sensors, etc., a whole line of products sold by Honeywell under their brand name Limitless that are I/O devices. In building automation, we have a standard that has been existing for some time called BACnet. The frequently used version of BACnet has been a wired application using Echelon Lawnworks as the wireless technology. And recently, there has been a movement to apply BACnet to general wireless technology, and very typically, they have used Wi-Fi as well. There's another application in building automation, or another technology being used in building automation, which is Zigbee. And that defines improvements over the operation on IEEE 802.15.4. And specifically, Zigbee adds meshing, and it adds a set of protocols for applications such as meter reading and remote controls. So these are areas of development within the building automation area. So we have two basic paths of being used in that particular area for wireless applications in buildings. Now, there are some emerging technologies in wireless that are being used at some of the other frequencies that have some characteristics that give that longer distances and greater penetration through concrete walls at 433, 915, or 908 megahertz. These bands have been reserved in North America for unlicensed use, but are not so designated throughout the world. 433 megahertz is particularly used for RFID, and we see it being used today for highway toll collection and public transportation fare collection. But the application with industry now is where it's being used as a shipping container content for inventory and tracking for shipping container information. This is where many different items are packed into a single shipping container. There's another technology to keep our eyes on that is in ocean. Sometimes the protocol that they use is called -7. And that's being used at the 915 megahertz band in North America. Or that same radio is also retuned to 868 megahertz for use in Europe. And that's being used in building automation areas. So the standards, basically the most widely used wireless standard in the world is Wi-Fi 802.11. And then for our industrial use, we see a broadening use of IEEE 802.15.4 with the additional protocols being assigned, typically at layers above the basic radio, as ISA 100 for wireless HART, and also some Zigbee applications. Notice that all of these radios are based on 2.4 gigahertz ISM band, and that is reserved for license-free operation throughout the world. Now, what about the rest of the world? What about the plant outside? What about the area outside the plant? I'll turn that over to Brian for further discussion.
Great. Thanks, Dick. Yeah, that was very interesting to see what work the standards committees have been doing, and clearly they have been quite busy. So I would like to chat for the next few minutes about, or the next little while, about what we do outside of the plant, or when we have longer distance applications, such as SCADA networks, particularly in water, wastewater, as well as oil and gas wells or out in the production fields. There's first of all, I'd like to chat about some of the different frequencies that are available and some of their characteristics. For example, 2.4 gigahertz radios with 1 watt of transmit power can go approximately 7 miles if you've got a clear line of sight. However, if we keep everything exactly the same, but we just change the frequency to 900 megahertz, we can go a much greater distance. Now, in order to get line of sight, we have to have the antennas quite a bit higher above ground due to curvature of the Earth. So with a lower frequency radio, we can gain significantly greater distances. Now, if we go even lower in frequency and we drop to 450 megahertz, because the FCC and other regulatory authorities will allow us up to 5 watts of transmit power, we can go about 50 miles and we don't have to have line of sight. Now, I say that's sort of a rule of thumb. These numbers are just very general approximations. There's a number of factors that will impact it, but we need to throw some numbers out there to give you some points of reference to be able to compare different radio types. In the diagram down below, you can see the difference in attenuation of two radio waves passing through the same material. The higher the frequency, the greater the attenuation of that particular radio wave. So that's why 450 megahertz radios or 900 megahertz radios can go quite a bit farther and penetrate through more houses or trees or buildings than can the higher frequency radio systems. So we get much better object penetration. Now, when there are no physical objects, or I should say, visible objects, and we just have a clear line of sight, then the obstructions in the path are air molecules that we are dealing with. So we still have some obstructions with line of sight. It's just air molecules, which are, of course, far less dense and therefore offer far less attenuation of radio waves. Okay. Now, in comparing the three most common ISM bands, a couple of things to be aware of. As we just mentioned, the lower the frequency, the greater typically the greater the distance, and that's because we have much better object penetration ability. However, the 900 megahertz license-free band is only 26 megahertz wide. When we compare that to the 2.4 gigahertz band, it's 81 megahertz wide, and that has implications of the number of users that can use that frequency band simultaneously in the same area, just by using different slices of the spectrum. And lastly, we have the 5.8 gigahertz band, which is one of the more recent designated ISM license-free bands. And if we have a relatively short distance, this can often be an excellent choice. The reason being, there just aren't as many products out there that utilize this band, and therefore we typically see less interference. Okay. Now I want to talk about when we decide a license-free radio is best, and the next slide will take the opposite tact and discuss why a licensed radio is sometimes best. Now, one of the first things is I mentioned earlier, I talked about 450 megahertz frequency band. Those are licensed frequency bands. And sometimes we have a relatively short distance application where we don't need the long range of a licensed radio system. And in some cases, what that means is that the radios are very close together, the signal will be very strong, and therefore that means we'll have a very high signal-to-noise ratio. Now, even if that noise floor does get higher and higher as more and more users install radios in that area, as long as the signal is proportionately high, then this radio can operate with 100% reliability and have no impact on other, will be not affected by other radio systems. The key here is the signal-to-noise ratio. As long as that ratio is maintained, then these radio systems can operate reliably. Now, in some areas, we may find that the 450 megahertz band is entirely occupied. Some areas like that include Los Angeles and other major cities, Chicago, New York. It's very difficult to get a license simply because the FCC has already allocated all of its licenses to existing users. So sometimes you end up on a waiting list for a couple of years, and if that is insufficient, that is when customers begin to consider a licensed free radio system. So availability of frequencies. Now, the FCC in the U.S. has made some efforts to address that. They have just gone through a rebanding initiative whereby everyone who is given a 25 kilohertz slice of spectrum in the 450 megahertz range had to drop that down to 12.5 kilohertz, and therefore it doubled the amount of spectrum, new spectrum that was available. By the way, just to clarify, when I say a 450 megahertz radio, I'm really referring to approximately 400 going up to about 512 megahertz. It'll vary from country to country which frequencies are granted to industrial users, but that is the broad range. So when I say 450, I really mean a very broad range of licensed radios centered approximately around 450. Okay, some of the other considerations to keep in mind here with licensed radios is the very narrow band typically means very low throughput. Some common numbers are with a 12.5 kilohertz slice of spectrum allocated to you, you can achieve an over-the-air data rate of 9600 baud. Comparably, is when we double that spectrum, we double the baud rate. So this has implications for industrial protocols that like to communicate with baud rates in the megabits per second. Also, wireless video is not possible or would be extremely slow at those levels of throughputs. So sometimes a licensed radio just won't quite do the trick. Then we have to think if repeaters are employed, the throughput will tend to drop a little bit further because these radios are, virtually all radios on the market are half duplex. Unless the manufacturer has just packed two radios into one enclosure and has two antennas, that's about the only way they can get a full duplex repeater system. The other issue why license-free radios are sometimes preferred is that there is no paperwork, no fees, and no delays associated with that. For a little bit of background, the process to acquire a license to operate a licensed radio from the FCC in the U.S. and in Canada it will be similar, and most other countries I would expect it would be similar as well, is that you typically hire a frequency coordinator, a company that knows how to fill out all the paperwork and is familiar with radio technology. You hire a frequency coordinator, pay them a few $100s, they make the application to you, then you usually have an application fee, and then there are some annual fees associated with it. The fees are not particularly high, but just to be aware of it, there is some cost involved. The time frame to get that, well, it varies. You know, these are bureaucratic organizations, you could say. But I would think a couple of months would be a reasonable time frame to secure a license from the FCC. So there are some regulatory or paperwork issues associated with acquiring a licensed radio, which you do not have to do so with a license-free radio. License-free radios, the manufacturer submits the product to FCC for testing, and FCC grants them an approval upon successfully passing the testing, and the product is assigned an FCC ID, which must be stamped on the outside of every radio product. So the manufacturers look after that. Once you have that FCC ID, you can now install and operate that radio anywhere in the country. A last and probably somewhat minor concern, although if you're the fellow installing these antennas, you'll certainly appreciate it, is that higher frequency radio antennas are typically much smaller and much lighter. I've seen some 450 megahertz antennas, and there's also a licensed band in the 150 megahertz range, and the lower the frequency, the larger the antennas must be. So if you're looking at some 150 megahertz antennas, you'll typically need a crane or some mounting apparatus to hoist the antenna up to the top of a tower or the top of a roof. Whereas with 900 megahertz, 2.4 gigahertz, or 5 gigahertz license-free antennas, they're very, very small. They get smaller as the frequency gets higher. You can easily carry these in your hand if you're in a bucket truck about to install one of these antennas. So it's lesser consideration, but again, the electrician who's installing it will always appreciate that. Okay. Now we chatted a minute ago about bandwidth and the relationship with throughput, and it's somewhat proportional. This slide is showing some different frequency slices of spectrum that some radios use. Now these would be in the license-free bands where we have a lot more spectrum available to utilize. For example, if a radio utilizes a 250 kilohertz channel, a typical over-the-air data rate would be 200 kilobits per second. When we talk about Wi-Fi radios in our laptops and Wi-Fi hotspots, they utilize 20 megahertz channels and are able to accomplish an over-the-air data rate of 54 megabits per second. Double that spectrum, and you've probably heard of the turbo mode that some hotspots offer. That can do up to 108 megabits per second. Now these numbers are just approximate. There's different modulation schemes that are being invented by wireless manufacturers all the time, and they are gradually improving the efficiency of their operation. In other words, getting more data through on a narrower slice of spectrum. So the numbers that I offer here, these are just representative to give some ballparks. And please keep that in mind with many of the numbers that I will throw out today. We all need some starting points to be able to make some measurements or compare one technology to another. So these are just meant in general terms. Okay, now I'd like to talk about when licensed radios are preferred and are the better option. Well, the very first consideration is that FCC caps 900 and 2.4 gigahertz radios in the U.S. at 1 watt of transmit power. And in Europe, they cap the 2.4 gigahertz band at 100 milliwatts of transmit power. So sometimes the distance just isn't great enough. So for example, if we need to go more than 20 miles here in North America, well, a licensed radio is pretty much about the only option because they do permit you to have higher transmit power. Now, another reason is that some customers prefer the security, the government regulatory authority, that they will not grant anyone else permission to use your frequency in your one geographic area. So that means that you'll be the only one in town, so to speak, who can operate on that particular frequency. And of course, that does work quite well in some circumstances, but there's typically two types of interferers in the licensed bands. And they are accidental interferers who don't know that their radio is transmitting or have just made an error. And those ones are usually very easy to track down because they don't know that they're causing a problem until you contact them, and they're usually quite willing to make the changes. And of course, FCC will enforce that for you on your behalf. But the other type of interference that causes a little bit of havoc in the licensed band is those who know that they are operating illegally. Sometimes this does occur, and those users, if they know they're operating illegally and they have the ability to move around, can be very difficult to triangulate on. So interference is mostly guaranteed, but the reality is, it's possible. Every now and again, we do run into somebody who has had some issue with a licensed band. But for the most part, in theory, it should work flawlessly. Now note that radios in the ISM bands would have no effect on licensed radios. And this is because they're operating at different frequencies, and all radios have filters inside of them to keep out interference at frequencies other than the one they are listening on. Okay, the next one is better object penetration at the lower frequencies. Now, we chatted about this earlier, but this means that you don't necessarily have to have line of sight. You can have the antennas mounted much, much lower to ground. And that, of course, reduces the cost of building a antenna tower and hiring somebody to climb up that tower with an antenna and mount it some distance above ground. So we don't have to mount the antennas typically quite as high above ground. Now, the 150 megahertz frequency band tends to curve with the Earth quite well, and the 450 megahertz band somewhat less so, but it curves through diffraction. In other words, diffracting off of roofs or buildings or trees, and is able to curve with the Earth to a limited degree. The higher frequencies, the 900, the 2.4, the 5.8, generally do not curve, so these radios will typically require line of sight or one antenna to see the other. Although for shorter distances, we can easily penetrate objects. What it really boils down to is the density of molecules separating one antenna from the other. Solid objects like houses and buildings and all that obviously have a much higher density. Air molecules are much more loosely spaced. So that is what we are referring to here. Okay. The next thing to think about are how we design that radio link once we have decided that I need either high throughput and I'm going to go with one of the ISM band license-free radios, or I can make do with low throughput, or I have a low bandwidth application, but I need some significant distance, or maybe there's just a whole ton of trees that that are in the path, and I've decided roughly what frequency band to use. The next thing that I'd like to chat about is the methods of designing a radio link. The best method is to test on-site with the exact radios you plan on installing, with the antennas at the height that you plan on mounting them. And in this photograph, this is a typical test kit that virtually all manufacturers of wireless products have something similar to this. And it just consists of a couple of radios, usually battery powered, a couple of antennas, so that you can take one radio to one site and then walk or drive to the remote site and then test the radio link with all of the obstructions that are already in place. Test it actually on site. This by far is the most accurate method of planning a radio link. Right off the bat, you'll know whether it works or it doesn't. The second is to measure the interference levels, so you have an idea of what else is out there operating in your frequency band. And then moving on from that, there will be cases where the distance is too great and the antennas have to be mounted too high above Earth to allow for curvature of the Earth or to clear trees or houses or other obstructions, and you don't have a tower already available that you just climb up and do the test on. So this is where we use a propagation software program. I'll chat about that in just a minute, but I also wanted to chat about the other end of the spectrum where some radio links are just so short that after you've had a little bit of experience with these sorts of things, you can just ballpark and say, yep, that'll work, piece of cake. It's too short for any source of interference to knock out that signal because the signal will be so strong and it'll maintain a very high signal-to-noise ratio. So sometimes we can just ballpark it when the distances are very, very short. Now on the other end of the spectrum is where we use something called path loss software. And what these are these programs that will predict the received signal strength of a radio link, and they will also estimate the required antenna heights. And this allows you to do a feasibility study. For example, if one antenna only needs to be 30 feet off the ground and you have a two-story building that you can mount the antenna structure to, that's usually very economical. However, in some cases it may say that the opposite end of the radio link needs to be 150 feet above ground. And if there isn't an existing structure, well, that's going to have some cost implications associated with it. So these will act as the feasibility study so you can cost out the entire network before you begin to purchase hardware or erect towers or this sort of thing. So these are great tools to allow you to predict the radio propagation. Now what these tools have, their secret, is that in addition to all the formulas and the math associated with calculating radio propagation, they also contain the topographical data for the area in question. So they know if there are trees in the area, which is you can see as the blue and green vertical lines, and they will take into account all of the dips and hills in the terrain in their calculations. So these are practical on radio links of about 2 miles or more. And we can design entire networks using this type of software. Okay, now one of the things I've had customers comment on is where they come, they approach us and they say, I need high throughput and I need long distance. And this is where we're seeing cellular modems become more and more popular as cellular technology or cell reception has become ubiquitous, almost everywhere it seems. And what they do is you can access these cellular modems from anywhere in the world from the internet, as long as you have an internet connection. So that really does eliminate any distance issues associated with point-to-point radio links. Or you could access one cellular modem from another cellular modem on the same carrier. So that could get you a very significant distance as well. Now they have a number of security methods that they utilize to make sure that the data is yours and you only can see it, such as GRE tunnels, demilitarized zones. IPsec is considered probably one of the most secure methods out there, as well as setting up VPNs, which are the same as what we use with our laptops dialing in remotely into our home office. Keep in mind, these require a SIM card and a data plan. Monthly charges. There will be a small fee associated with deploying these, but we can get some pretty high speeds. Even with 3G, we can do 14.4 megabits per second, which is fast enough for wireless video, as well as having other equipment connected like PLCs or other Ethernet-based equipment. So once you have looked at a point-to-point radio link, if there's any significant costs or if you have to erect towers, it's worthwhile doing a business case to evaluate if cellular should be used. And here's the easiest part of it, is that a site survey is just done with your phone. If you get half-decent reception on your cell phone, well, that tells you that the cellular modem would work just fine. And the beauty is that these cellular antennas, they're a couple inches tall. They can be mounted right on top of the electrical enclosure that the modem is mounted inside of. And so it doesn't involve climbing up to the roof or mounting anything on towers or this sort of thing. So here's one application where this turned out to be a perfect solution. This was in Wyoming. A company involved in fracking had a number of storage tanks of fracking fluids located all over the state. None of these locations were particularly close to each other, so a point-to-point link was out of the question. And they wanted to get that information at their head office. So from their head office, they can dial out to each of these remote sites. They had a level sensor mounted on the top of the tank with an Ethernet output. I think it was Modbus TCP. And they're able to get the data back to their head office and determine when they needed to dispatch trucks to refill these tanks. So that was a very interesting application that we did. Now I want to show some examples of hybrid wireless projects that we have done. In this case, this was an area where they had a number of pump jacks pulling oil out of the ground, and they were all a couple of miles from their SCADA master site. So this was well within range of 900 megahertz license-free radios. So they used 900 megahertz to get the data back to the SCADA master. But there was one site that was simply too far away, where they could not establish a point-to-point radio link, but there was cellular coverage. So they took a I/O module, wired it into a cellular modem, and had that cellular modem use the cellular network to get the data back to the SCADA central site. So it was an interesting solution where we combined a couple of different technologies because there was no one-size-fits-all there. Next, I wanted to show how we did voice over IP with involving 2.4 gigahertz, 900 megahertz, and a cellular backbone in this network. In this particular case, the customer wanted to have voice communications out to their remote site. So they had located some voice over IP handsets that used Wi-Fi. And this gave them the ability to roam around this particular site. So we set up a 2.4 gigahertz access point and connected it to a switch. And also connected to that switch was a long-range 900 megahertz Ethernet radio system. And they also happen to have a PLC using Modbus TCP that they also wanted to gather the data from. So they piggybacked the Modbus TCP data and the voice data onto a 900 megahertz radio link, shot it back a couple of miles to where they did have cellular reception, and then they set up a GRE tunnel between these two cellular sites. And I believe it was about 150 miles away where their head office was. They were able to communicate directly via voice with the head office, as well as extract Modbus TCP data from their PLCs. And the customers told us that for the voice communications, there was approximately about a 1-second delay in communicating. So they considered that entirely suitable, and we're quite happy with that solution. Okay, just wrapping things up here, I just wanted to chat about some of the experiences that I've had out in the field of traveling the countryside and helping customers troubleshoot their systems. And I wanted to just relate some of the key experiences that I've had. And one of them is to not to wait until after you've installed the radio system to measure interference levels. Measure the interference levels beforehand. It will allow you to select which frequency bands, the antennas, the equipment, the transmit power, design the entire system to have a suitable noise floor. And sometimes that involves getting in a bucket truck and elevating yourself 70 feet above ground. Got a laptop in one hand, a little spectrum analyzer that plugs into the USB port on the other hand, and a pole with your antenna mounted on it, and making some interference measurements or sweeping the spectrum for different sources of interference. Very important to do that beforehand rather than after when a problem has been reported. Next is to measure and document received signal strength levels on the installation date to have a benchmark for future troubleshooting, so you can then compare it and see if equipment is degrading over time, or foliage is increasing the attenuation of your radio signal or whatnot there. The next thing to keep in mind is that lower frequencies, not only do they penetrate objects better, they also bounce better. So this means that if we have an application, say in a refinery or a tank farm with all kinds of steel structures, metals reflect radio waves very well, by the way, is that the lower frequency will get better reflections and therefore better distances. Next thing to keep in mind is not to overload that 450 megahertz Ethernet link with video. Video is a very high throughput, and some people see an Ethernet port on a product, and next thing you know, a video camera is plugged into it. So let's be careful of that sort of thing. Then do a business case to see if cellular would be less expensive than point-to-point links, which might require building some towers. So it's always worth it to make sure you do the business cases in advance. And one of the things I found is because 2.4 gigahertz is used in a lot of consumer products, most notably our laptops, it can be problematic near hotels or apartment blocks, or generally areas with lots of people. On the other hand, inside of large warehouses where you can control the number or types of radios that are being utilized, they can work very well. But I've found that when you got lots of people around, lots of consumers, there can be some issues. Okay, lastly here is just for overall, this pretty much applies to any radio product for best performance considerations. Line of sight is always preferred. That just means fewer obstructions, less attenuation of the radio signal. Next is to mount the antenna outside of your electrical enclosure that's housing the radio system. That just means the enclosure is now one less obstruction in the path. Keep the antennas away from RF noise sources. This, I suppose, is fairly obvious, but variable frequency drives or other pieces of equipment that are going to generate RF noise will increase the noise floor. So we should physically try to keep our antenna away from those sources. Mount the antenna as high as possible. Again, that just decreases the number of obstructions in the path. Keep the coaxial cable as short as possible. Don't spool it up if you have an extra 20 or 30 feet remaining. Because the radio signal attenuates in the coax cable. The longer it is, the greater the attenuation. And when you're comparing data sheets from one manufacturer to another, look for the best receiver sensitivity. That equates to its ability to hear a weak signal. Next is, on the opposite end of the scale, is the transmit power, the ability to speak loudly. Pick a radio with the highest transmit power. It just produces the highest signal-to-noise ratio and gives you the highest level of reliability. Then be careful about the type of antenna and the gain that you select. Make sure you select them appropriate for the installation. Usually that means a high-gain antenna there. Then we have antenna separation. Always a good idea to keep one antenna system separated from other antennas. This is considered a fairly big requirement, and there's different distances that are required, but all these radios have filters in them. Filters can be overwhelmed if a signal is powerful enough. So even if radios are operating at different frequencies, always a good idea to mount them some distance apart. Okay, well that's it for my session there, and you've got my contact info on this slide here, and we've also got Dick's contact info here as well if you have any questions. And Dick or Stacy, I'll turn things over to you.
Great, thanks, Brian. Okay, we've had some great questions come in so far, and I just want to encourage everyone to submit any questions you may have into the Q&A box and join our discussion. So let's jump into it. Can any of the standard networks use one of the licensed frequencies?
Well, it sounds like it's probably directed to me. Let me mention something about the standards. As I said before, the entire standards document is written around the use of a specific frequency. Now, when we wrote the ISA 100 standard, we explicitly separated the physical layer from the rest of the standard. So it would be possible for a supplier to implement the entire ISA 100 standard on any available radio. The only thing is, of course, that because we have depended on the IEEE 802.15.4 chip, which has the built-in security codes, then the new radio would have to have, would also have to supply that capability as well. But other than that, the entire standard will operate on any available radio. And we did that for the future, but obviously, if somebody wanted to apply the ISA 100 standard at 900 megahertz, they certainly could do that. Brian? Do you have any comments?
Yeah, great. not too much to add there, but yeah, that pretty much covers it as far as I'm aware.
Okay, great. If multiple HD video cameras from remote areas is a primary goal, what approach would you take? And keep in mind that hardwire versus wireless considerations with infrastructures need to be kept in mind.
Sure, maybe I could address that one. Well, it would depend upon the distances involved and what the total objective was. For example, if you want full motion video at higher resolutions, then that's going to require a lot of bandwidth. So we'd have to think about how many cameras we wanted to connect to a single radio system and what the environment was like. If this is shooting across a forest or a rural area or something like that where there's not anticipated to be much interference, and the distances are not terribly great, say less than, 5 or 6 miles or something like that, then we could probably do it with a point-to-point radio link in one of the ISM bands. If the distances get much greater than that, well, we'd have to think we could possibly do it with 1 or 2 repeaters in the path. And I would think we should still be able to have enough bandwidth, even with 1 or 2 repeaters in a path. But again, it just depends on how much interference is likely to be in that area. If the distances go much beyond that, well, the only options really are going to be probably cellular or something of that sort. It's just the licensed radios, they're just not going to have the throughput to be able to do wireless video, especially anything high definition or with any reasonable frame rate.
Thank you, Brian. This attendee commented that it would be less than 5 miles and 10 to 20 cameras, so approximately 10 FPS.
Oh, frames per second, sure. Yep. Oh, there we go. Okay, I see that now. Yep. So that sounds like it would be entirely doable. What we would have to do is just measure the interference levels in the area and find out which frequency band, but I would probably recommend one of the license-free bands. We could probably do this in 900, 2.4, or 5 gigahertz, depending on the interference in the area. We would just have to use one of our little spectrum analyzers, these little USB-based devices, make a couple of measurements, and I would think that would be something we could certainly do.
Okay, great. In your experience, when replacing an obsolete and outdated analog radio system with a digital system, is the replacement system more likely to be licensed or unlicensed?
Well, that depends on the application, and I think that has been sort of an overarching theme of our presentation today, is that the frequency selection and therefore the type of radio really depends upon the application. If they were short-range applications, then we could probably do it possibly with one of the standards-based radio systems. If it's a longer-range application, then we might have to look at either a lower frequency radio system or something with some much higher transmit power. So again, I guess it depends on what kind of throughput they are looking for and what the approximate distance is. Further complicating that is that a lot of new products now come with Ethernet ports on them, which are demanding higher throughput. So then we would need to have a look and see if it is something like connecting 2 PLCs, which will require much higher throughput, or if it's just picking up a couple of I/O points. So there's a number of questions. This does boil down into more of a discussion where we would have to have a number of other questions. And also, if we're going to look at the license-free radios, we'd need to make sure there isn't too much interference, that we can successfully operate these radio links as well.
Great. This is a cellular question. What kind of reliability or availability can we realistically expect of modern cellular infrastructure? And apart from signal strength, what else should we be measuring to try and determine this?
Well, signal strength is a key measure, but there's also a measure of noise in the area that more sophisticated cellular devices will report what the signal-to-noise ratio is. And what that's looking at is how many other users are utilizing the cellular network at that time. Generally, we've seen very high levels of cellular reliability. It will depend upon a number of factors. There will be some things such that will be out of the control of the engineers that installed the system. They would be things like if a lightning strike hits the tower that your cellular modem is communicating with, or other factors. So I would suggest that the factors that we can control will lead to extremely high levels of reliability. It will almost always be the factors that we can't control, like lightning strikes or other power outages. Well, they have backup power on most of these cellular sites, but there would be usually factors out of our control that would then influence the reliability.
Okay, great. Well, these have been some fantastic questions, and I just want to thank everyone for participating. If you missed any portion of this webinar, or if you would like to watch the recorded version, we will be emailing all registrants a link to the recording, along with additional links and resources for supporting information. So be on the lookout for an email from me in the next few days. This concludes the To License or Not to License, Selecting the Right Frequency for Your Application webinar. Thank you to everyone for attending, and we hope you acquired useful information and hope to see you again in one of our future webinars. Have a great day, everyone.